Okay.
So hello and welcome to session 109 of our online seminar on PDs and applied mathematics. It's my great pleasure to introduce today's speaker, Professor Oana Pocovnicu. She is a professor at the Department of Mathematics at Heriot-Watt University in Edinburgh, and she's also a member of the Maxwell Institute for Mathematical Science, there also in Edinburgh. Her research focuses on nonlinear PDs with significant recent contributions to probabilistic analysis of dispersive equations. And today, she will present her talk on invariant Gibbs dynamics for fractional wave equations in negative Sobolev spaces. Welcome, Professor.
Thank you very much. Thank you very much, Professor Fedderson, for such a nice introduction. And also, I'd like to thank Professor Limaco and then all the organizers for the opportunity to speak and the kind invitation. And I'm very excited to be part of this seminar. Before I start my talk, maybe let me mention that it's based on a joint paper with Luigi Forcella, who was a postdoc here in Edinburgh a few years ago, and who's now a tenure track professor at University of Pisa in Italy. My goal today will be to talk to you about the class of fractional wave equations. I'll try to focus on the solution theory for these equations at very low regularity. So by this, I mean in negative Sobolev spaces. And you'll see in the talk that there's not that much that can be said at such low regularities from a deterministic point of view. However, if one adapts a probabilistic perspective, namely considering random initial data of low regularity, then one can talk about almost sure local well-posedness and almost sure global well-posedness. So I'll try to convey to you how this perspective, a probabilistic perspective, can be very useful when we discuss solution theory at low regularity for such dispersive models. So I'll start by presenting to you the equations. So I'll try to explain each of the words in this kind of long name, the focusing fractional nonlinear wave equations. So first of all, if you look at these equations and you take alpha equal 1, and then maybe also forget about this 1 here in front of minus the Laplacian, then you notice that this is just the D'Alembert operator, which appears in the wave equation. Okay, however, alpha for us is not 1, is a number strictly between 0 and 1. And because of this kind of fractional power of minus Laplacian, we say that this is a fractional wave equation. Now, the fact that I have this 1 here makes this equation not really be a wave equation, but more like equation that sometimes people call Klein-Gordon equation. However, for simplicity, I'll still call it a wave. In terms of nonlinearity, here we consider any odd power nonlinearity, so 2m plus 1, where m is an integer, which is at least 1. And we look at this equation on the two-dimensional torus. So u here depends on the space variable x, which is in the two-dimensional torus, and the t, which is the time variable, which is in R. And we only want to study real valued solutions. So u here is real valued. Okay, so this is the model, and the initial conditions U0, U1, as I was trying to say earlier, we take them in negative Sobolev spaces. So they belong to HS time HS minus alpha, where here S is negative. And since maybe not everyone is maybe familiar with this notation, just so that we are all on the same page, here HS denotes a Sobolev space, which is endowed with this norm here, where f hat of n is nothing else than the nth Fourier coefficient of f. So defined in this way here, the nth Fourier coefficient. Okay, so essentially what we want to say in this definition is that we want to put 1 minus Laplacian to the power s over 2 of a function f to be in L2. And if this happens, then we say that f is in HS. Okay, so this is my setting. So this is the equation. We want to study it for initial conditions in such Sobolev spaces HS for S negative. Okay, so maybe the first question to answer here is, what do we mean by a solution of such a nonlinear PDE? So as it is typical for dispersive nonlinear PDEs, by solution we mean a solution that is given by the Duhamel's formula that I wrote here. Okay, so what is this formula? You will recognize maybe if you replace alpha by 1, this would be just a solution of a wave equation. So if you remove this integral, it's going to be the solution of the linear wave equation. With this Duhamel integral, it's a solution for the nonlinear wave equation with nonlinearity u to the power 2n plus 1. And if you are not kind of familiar with this Nabla notation, all I mean by that is that when we look on the Fourier side, so if you take the Fourier coefficient of u at n, then this Fourier coefficient is given by what's written on this second line, right? So, cosine of t Nabla to the alpha u0 simply means that on the Fourier side, you would have cosine of t n to the power alpha times the Fourier transform of u0 at n, okay? Where this n with this Japanese bracket simply means square root of 1 plus n squared. Okay, so this is what a solution means. It's given by this Duhamel's formula. Now, what do I mean by well-posedness in the deterministic sense? The fact that, say, this fractional nonlinear wave equation is locally well-posed in HS, that means that for any initial condition, U0, U1 in HS, there exists a small time, capital T, and a solution of the equation belonging to this space here. So it's continuous from the interval 0t with values in HS. We also want the solution to be unique, and we also want the solution map to be continuous with appropriate in the appropriate topology. Okay. And now if we talk about global well-posedness, we want to be able to say that the local in time solution that we previously defined exists, in fact, for any time capital T. So it's not only for a short time, so from 0 to capital T, but in fact, we can define it from 0 to any time T. Okay, so really my goal here is to try to understand the local well-posedness and the global well-posedness of this fractional wave equation. And in fact, you'll see that we're not really going to be able to say something about this equation, but we'll need to renormalize the equation in order to say something meaningful in terms of solution theory. But for the moment, let's maybe go back to what's known in terms of deterministic analysis, and even to the simpler case of alpha equal 1. So alpha equal 1, once again, this would be just the nonlinear wave equation. So there's no kind of fractional dispersion, alpha equal 1. So for this equation, right, deterministically, it is known that it is ill-posed at negative Sobolev regularities. And this goes back to a work by Chris Colliander and Tao, and also to more recent works by Borsia, Okamoto and Svetkov, and Forlano and Okamoto. Okay, so this being the case, what we expect is that also for alpha less than 1, but sufficiently close to 1, the equation, the fractional wave equation, should still be ill-posed at negative Sobolev regularities. So this means that in some sense, we reached the limit of deterministic analysis. Deterministically, the equation is ill-posed at such low regularities. So there's not much we can say deterministically. That's why we adopt a probabilistic point of view, and we try to understand if through this probabilistic point of view, there's still something meaningful to say about solution theory. And this idea of kind of going beyond the limits of deterministic analysis using probabilistic tools, it's an idea that goes back to works by Bourgain from 96, and then later on Björk and Svetkov in 2008, and Colliander and O from 2012. Okay, so as I was saying earlier, I'm going to consider this equation, and in fact, it's a renormalization with random initial data. And the goals of the talk will be first to construct the Gibbs measure associated to this equation. Secondly, we're going to talk about the almost sure local opposedness of the equation with such random and rough initial conditions. And lastly, we'll use the first two parts. So we'll use the Gibbs measure and the fact that we already have almost sure local opposedness to extend these local in time solutions globally in time. This last part will be very short, and I'll very briefly kind of tell you the method, which is again a method going back to Bourgain. So we'll discuss this later on. Okay, so let me start with the construction of the Gibbs measure associated to this fractional wave equation. So I'll go back to what's known in the finite dimensional case for finite dimensional Hamiltonian systems, so that you understand what the idea behind the Gibbs measure is and the construction of the Gibbs measure is. So the equation that I presented here turns out to be a Hamiltonian equation. So if you introduce a new variable v, which is just the time derivative of u, then you can write the equation in this way, where h alpha is the energy, or the Hamiltonian defined here. So this h alpha of uv has this kinetic part, which is essentially the h alpha norm of u plus the L2 norm of v. And it also has this potential part, which is the L2m plus 2 norm of u. And because of this Hamiltonian structure, this energy is conserved by the flow. So if you compute h alpha at time t, so u of t dt u of t, that will be the same as the energy at the initial condition u0, u1, and that holds true for any time t. Okay, so the fact that the equation is Hamiltonian, it's extremely important. Okay, so now let us go to the case of finite dimensional Hamiltonian systems. So let's assume we have a Hamiltonian which depends on this variable P1 up to Pn, Q1 up to Qn. And then let's consider this Hamiltonian flow given here. So Pj dot is the derivative of h with respect to Qj, and Qj dot is minus the derivative of h with respect to Pj. we notice that the vector field on the right-hand side of this system, so dH over dqj and minus dH dpj, is divergence-free. Therefore, if we use a classical Liouville's theorem, we can show that the Lebesgue measure, this finite dimensional Lebesgue measure, is invariant under the flow, under this Hamiltonian flow. Moreover, because of the Hamiltonian structure, this Hamiltonian is also invariant under the flow. So for finite dimensional systems, the Gibbs measure is simply what is written here. So it's exponential of minus beta times the Hamiltonian. Beta here is just a constant. You can just take it to be 1, times the Lebesgue measure, times this constant, which simply renormalizes the measure to make it a probability measure. So because the Hamiltonian is invariant under the flow and also the Lebesgue measure is invariant, this Gibbs measure will be invariant for this finite dimensional Hamiltonian flow. And we also have global well-posedness. Okay, so this is what happens in the finite dimensional case. We have such an invariant Gibbs measure. And why are such measures, invariant measures, important? That's because they give us some qualitative information about the flow that would otherwise maybe not be so easy to obtain. So let me explain this on this slide. So assume we have, as in the previous slide, such Hamiltonian dynamics with an invariant measure. Then we can view the system as a dynamical system with a measure preserving transformation, capital T, where T is just a solution map that to an initial condition, P of 0, Q of 0, associates the solution at time 1. Okay, so now, once we are in this kind of situation, there are some recurrence, very nice recurrence theorems that hold, namely these two, Poincaré's recurrence theorem and Furstenberger's multiple recurrence theorem, which say the following thing. So for the first one, Poincaré's theorem, it says that if you start with an initial condition in a set A, which has positive measure, then with positive probability, you will return, so your flow will return to the same set. And moreover, if you look now at the Furstenberg's recurrence theorem, same situation, you start with initial conditions in a set of positive probability, and then say you take a positive integer k, the theorem says that, again, with positive probability, you will return to that set k times. Okay, so obviously these are very nice qualitative properties of the flow. That would be maybe very kind of difficult to obtain without such theorems. Particularly if we talk about infinite dimensional situations, so if we talk about PDEs. So this is really the question here. Can we construct invariant measures now for Hamiltonian PDEs, so in infinite dimensions? And then in this talk, I'll be focusing on these fractional nonlinear wave equations. Because as you see, if we can obtain such invariant measures, then we are exactly in the setting of Poincaré's theorem and Furstenberg's theorem. So we'll get these nice recurrence properties of the flow. Okay, so now let's come back to our fractional wave equation and see if we can mimic what we've seen in the case of the finite dimensional Hamiltonian system in our case. So once again, this fractional wave equation is Hamiltonian, and the Hamiltonian is, I rewrote it here. It's conserved, so it's invariant under the flow. So we would like to construct a Gibbs measure exactly as in the previous slides, writing it as exponential of minus this Hamiltonian du dv. Okay, and somehow we would, we expect, as in that case, that this would be invariant. However, we're already writing things very informally here, because there's no such thing as du/dv. We know that there's no infinite dimensional Lebesgue measure. Right? So du/dv, as it's written, doesn't make sense. So to overcome this, the idea is to write the Gibbs measure as a weighted Gaussian measure. So the potential part of the Hamiltonian, I write it here in this exponential as a weight. And the kinetic part of the Hamiltonian, I will write it in the part of the Gaussian measure. So it will go into this d mu alpha, right? So this is the kinetic part of the energy corresponding to U, and this was corresponding to V. And now these two measures here, so this one and this other one, they are legitimate measures. So there are the classical Ornstein-Uhlenbeck measure for the U part and the White-Noyd measure for the V part. Okay, so we overcame this fact that we don't have an infinite dimensional Lebesgue measure. Okay, but still, the question remains, okay, with this potential part as a weight, is it still possible to make this measure into a probability measure? Because that's really the goal, to say that, you know, there is a constant z such that this measure can be renormalized to be a probability measure. Okay, so let's try to understand that, and to understand that we need to discuss a little bit more about mu alpha. Okay, so I'm rewriting it here. So formally, I think of this d mu alpha somehow on the Fourier side as being this kind of infinite product of measures. Right, I'm just writing, all I'm doing here is basically writing these Sobolev norms on the Fourier side. So they correspond to some infinite sums, okay, which give me this infinite product. But of course, this is only formally. Rigorously, this mu alpha is in fact some put forward measure or probability measure induced by this map here, where G0n are independent standard complex valued Gaussian random variables on some probability space. They satisfy this kind of condition. That's simply because we want the functions that we obtain at the end of the day to be real valued. Okay, and I'm taking the variance of this JGN to be two, basically one for the real part and one for the imaginary part. Okay, so this is kind of maybe a better definition or more precise definition of this mu alpha. And it's also useful because it tells us that the typical elements in the support of this measure have this form, right? So this essentially have Fourier coefficients of this form, G0n over n to the alpha and G1n. Okay, so let's try to understand the regularity of these typical elements in the support of this Gaussian measure. So it turns out that, you know, as we kind of expected, they have negative Sobolev regularity. So these elements will belong to the Sobolev space HS for S less than this number. So it's -1 minus alpha. Remember, alpha is less than 1, so this will be a negative number. So they belong to this HS almost surely. And we can see this, at least somehow heuristically, with a very short calculation. So if you try to compute the variance of the HS norm of this, for example, U omega, let's just focus on U omega. Okay, we write what the HS norm square is. That's just the summation of n to the power 2s times the Fourier coefficients squared. So that's G0n squared n to the 2 alpha. Now, if you put the expectation inside, we know that the expectation of G0n squared is 2. Okay, so essentially we get this series, and we know that it's convergent if and only if this exponent here is bigger than the dimension. and the dimension is 2. Okay, and now if you do the calculation, you get exactly this condition. S has to be strictly less than -1 minus alpha. Okay, so this calculation together with some Chebyshev argument shows that U omega will be in such HS almost surely. And you can go even further and show that, in fact, again, almost surely, it will not have beta regularity. So it's in HS if S is strictly than this number, but almost surely it's not in H minus 1 minus alpha. Okay, so they are truly very rough functions. So this measure mu alpha is indeed supported of at these negative Sobolev regularities. Okay, well, in particular, because mu alpha is supported in such HS with S negative, the L2 norm of U will be infinite mu almost surely. And because we work on this finite volume domains, this also means that this L2m plus 2 norm is infinite almost surely, mu alpha almost surely. Okay, and this is bad news because when we try to construct the Gibbs measure, because this norm appearing here in the exponent is infinite, what we get is exponential of minus infinite. So that's that's 0. You cannot define this as a probability measure. Okay, so this heuristic argument shows that if we want to make sense, if we want to construct a Gibbs measure, we need to renormalize this potential part. We need to renormalize the integral of U to the 2m plus 2. So how do we do that? Well, we use the weak renormalization, which from what I understand is standard in physics. So I'll try to explain briefly in this slide what the weak renormalization is. So as we've seen, a typical element under the measure mu alpha is almost surely not in L2. So in particular, if you project onto frequencies, Fourier frequencies, which are at most n, so this is what this capital Pn means, is this projector onto frequencies at most n, then the integral of Pnu squared diverges to infinity. And in fact, we have kind of even more precise information. If we try to compute the variance of Pnu, we will denote this by this sigma alpha n, then using the definition of U, right, as being the summation of G0n over n to the alpha exponential INX, and using the independence of these G0j's and so on, we get that this variance is given by this series, this sum. And we see that the sum kind of diverges as n goes to infinity at this rate, capital N to the power 2 minus 2 alpha. Okay, so now how do we define the weak-ordered monomial Pnu to the power k? Well, is defined using the Hermite polynomial of degree k applied to Pnu, and with parameter sigma, exactly the sigma that we've described here. Okay, so what is a Hermite polynomial? Hermite polynomials are kind of defined using this relation. So if you expand this exponential, exactly you'll get the Hermite polynomials here. So just to give you an idea of what these are, I wrote the first five here. In particular, if you look at the Hermite polynomial of degree 2, that's just x squared minus sigma. So if we think of what the weak-ordered Pnu squared would be, that would simply be Pnu squared minus sigma, which it was just a variance of Pnu, or the expectation of Pnu squared. So you see what's happening here. The renormalized Pnu squared is essentially Pnu squared, out of which we subtracted sigma. We subtract the variance. So we subtract a quantity that goes to infinity, right? So in some sense, we subtract some sort of infinity here. Obviously, at higher degrees, so H3, H4, this renormalization is more complicated than just saying we're subtracting the variance. But I think this H2 or the PNU squared renormalized gives a good idea of what this weak renormalization does. Okay, so this is what the weak renormalization in general is for a monomial PNU to the power k. Now we are in the case where, that interests us. So we want to look at the weak ordered PNU to the power 2n plus 2, right? So once again, it's given by this Hermite polynomial of degree 2n plus 2. And the construction of the Gibbs measure really boils down to this theorem, which says that this integral of the weak ordered PNU to the power 2n plus 2 converge as n go to infinity in any LP of mu alpha, p between 1 and infinity. And one can define rigorously the Gibbs measure as being the exponential of minus this limit, so this limit of integral of PNU to the power 2n plus 2 renormalized. And this, at the end of the day, this will be indeed a probability measure. Because I don't have so much time, I'm not going to enter into the details of this proof. Let me just say that the proof uses a variational approach that was introduced recently in a work by Barashkov and Gubinelli. Now, I'm happy to give more details if anyone needs at the end of the talk. Okay, so notice that this happens for a certain range of alpha. So for this range of alpha, depending on the degree m of the nonlinearity, we were able to construct this Gibbs measure. Let us now move to the second part of the talk, which is about almost sure local well-posedness. So as I mentioned before, we consider the deterministic equation with random initial data. And as random initial data, I'm taking exactly the one that you've seen previously, which were the typical elements in the support of the Gibbs measure, right? So we already know that these are rough of negative regularity, and this also means that the linear solution corresponding to this initial data, that's also going to be rough. So in particular, it's not going to be in L2. It's not going to be a function. It's just a distribution. Okay, well, then that's problematic in the sense that in general, we don't know how to take product of distributions. So Z1, or the Z1 is this linear solution to the power 2n plus 1, doesn't quite make sense. And therefore, u to the power 2n plus 1 doesn't quite make sense. So this means that the equation as it is, with the nonlinearity u to the power 2n plus 1, we don't quite know how to make sense of it at negative Sobolev regularities. So this leads us to consider the renormalized fractional wave equation, which is exactly what you'd expect. So you take the weak ordered u to the 2n plus 1 instead of just the power u to the 2n plus 1. Okay, so the equation for which we try to understand the solution theory is in fact this one here. Okay, so now if we go back to Duhamel's formula, we see that this u has the form Z1, so the linear part of the solution, plus W, where W is just the integral that was appearing in Duhamel's formula. And if we substitute in this formula U equals Z1 plus W, we see that W in fact solves this equation. Okay, so what is the idea here? So this is also called the first order expansion. The idea is that we write our solution as the linear part, which is random and rough, plus this remainder W, which solves this equation with zero initial conditions. And it turns out that this W is actually smooth. It has positive regularity. And therefore, we can apply tools from deterministic analysis to do a fixed point argument for the W equation. So this is really our goal. It might sound surprising that suddenly I have this W that has positive regularity, but this situation actually occurs in different situations within the realm of nonlinear dispersive PDEs. Okay, so let me try to understand a little bit better what W is here. So when you try to renormalize Z1 plus W to the power 2n plus 1, because of properties of these Hermite polynomials, if you try to expand this, the renormalization actually only hits Z1 to the power L, which is quite natural because, as I said, W is supposed to be of positive regularity, so we have no interest in trying to renormalize that. So in fact, W will have this formula here. So it will be a summation Z1 to the power L renormalized times some other powers of W. So we want to understand this W and set up a fixed point argument for this equation for W. Okay, so this is what we'll do, and the result that we obtain at the end of the day is this one here, which says that given M, there exists a range of alpha, right? For M equal 1, which is the case of the cubic equation, the range is 5/6 and 1. For bigger M's, which means quintic equations and higher, the range is some number that depends on M up to 1. Such that the renormalized fraction wave equation admits almost surely a local in time solution at this negative Sobolev regularity. Okay, so this is the result. And as I said, we prove it by doing a fixed point argument for the W equation. Okay, now to set up that fixed point argument, we're using a tool which is quintessential within nonlinear dispersive PDEs, and that's the Strickard's estimates. So maybe for those of you who are not familiar with Strickard's estimates, let me very briefly say what these are. So Strickard's estimates go back to Robert Strickard, who proved the first Strickard's estimate in 1978. Since then, there's been a lot of work on these estimates. And here I'm citing a work of Van Dondien about Strickard's estimates for a fractional wave equation, which is our setting. So what do these Strickard's estimates tell us? They give us an estimate on the space-time integrability of a solution for a dispersive PDE, essentially. Okay, so what do I mean here by space-time integrability? Well, we're using this type of spaces, LP in time with values in LQ in X. Okay, so what would be this type of norm? I'm first taking an LQ norm in X for a function f, which depends on both t and x. Okay, the result is still dependent on t, so then I'm taking an LP norm in t. Okay, if you write this out carefully, explicitly it will be just this double integral. Okay, so now the Strickard estimates say the following thing for our particular context. So take this fractional wave equation with a generic capital F on the right-hand side, the initial conditions V0, V1. Then this LP in time, LQ in X norm of the solution can be bounded by some norms of the initial conditions plus an L1 norm in time, H gamma minus alpha norm in space of the right-hand side F, okay? And P and Q need to satisfy some admissibility conditions. Gamma has an explicit definition, but I don't want to go into these details because they are not really relevant. So, okay, so now that we have the Strickard's estimate, we're going to set a functional space, a Strickard space, which is this XS defined here. So the first component of it is L infinity HS, which is what you would expect, right? Because you want to have solutions at the end of the day which are continuous in time with values in HS. But here you intersect it with one of these three-card spaces. So it's not quite LP in time, LQ in X, as you've seen previously, but you also want to put S minus gamma derivatives in X, right? So this WS minus gamma is defined here. So it's basically LQ with S minus gamma derivatives in LQ. Okay, so just to understand what this is, so the first component, it allows you to put S derivatives, but it limits you to have integrability up to having integrability L2 essentially here. Whereas the second component, it only allows you to put S minus gamma derivatives, so you have fewer derivatives, but allows for more integrability. So this Q will be very large, right? Think at it about as being infinity or close to infinity somehow. So you have much more integrability, but the price you pay is that you have fewer derivatives at that high integrability. Okay, so now if you try to use this kind of space, not LP-LQ, but LP-WS minus gamma Q, so you add this S minus gamma derivatives, what you're going to obtain here will be this S minus alpha, right? So this comes from the fact that you added S minus gamma derivatives, plus previously in the three-card estimate, you had gamma minus alpha, so S minus gamma plus gamma minus alpha, it gives you this S minus alpha. Okay, so I'm just writing this because you'll see it appear on the next slide. So the idea here is we want to do a fixed point argument for W in this three-card space XS using three-card estimate and doing a case-by-case analysis, because you've seen that, maybe let me go back. For W is a sum of 2m plus 2 terms, so we need to treat them differently. That's why we have a case-by-case analysis. Okay, so that's good, but we also need to have some information on this random terms, so the weak ordered Z1 to the power L. And it turns out that the regularity of these terms is minus L times 1 minus alpha minus epsilon, almost surely. Okay, so now if we go back...
Professor, you have 3 more minutes.
3 more minutes, okay.
Yes.
Thank you. I'll try to wrap up. Okay, okay, since I only have 3 more minutes, I might not have enough time to go into these details. So maybe let me stop here with this part, saying that, as I said, we use the three-card estimate. You've seen this three-card space that we're going to use for W, and for the stochastic objects, we use this regularity. Okay, so now it turns out that we can improve this result in the sense of improving the range for alpha if we do what is called a second order expansion. So before we had Z1 plus W, now in W, we look at what's the roughest term. It's going to be this Z2, and we also set it aside. Okay, so we write the W as Z2 plus W2, and now let's try to do a fixed point argument for W2, and you'll see that in our estimates, I don't quite have time to show this here, in our estimates, we have better regularity, and that's really what allows us to extend the range for alpha. Okay, I'm sorry I don't have time to go over these details. So let me finish with the almost sure global well-posedness, just this one slide. So typically when we try to extend local in time solutions globally in time, we use the conservation law. However, at this very low regularity, there is no conservation law. So the idea is to use the formal invariant of the Gibbs measure to construct global dynamics. And The problem with this is that it kind of seems like a circular argument. So we want to use invariance to show almost sure global opposeness. On the other hand, to talk about almost sure global opposeness, or to talk about invariance, we need almost sure global opposeness. So how do we break this this circular argument? Well, the idea goes back to work of Bourgain from '94, who projected kind of the system onto the first and Fourier frequencies. So he has now a finite dimensional system, which will have a finite dimensional Gibbs measure, which is invariant. Obviously, global opposeness holds in that finite dimensional setting, and then uses an approximation argument to say that, in fact, this is also true for the PDE, so for the infinite dimensional. So we still have invariance and global opposeness. So I'm going to stop here with this part, just to say that the Bourgain's invariant measure argument is also applicable in this situation of the fractional nonlinear wave equation. So to conclude, for this renormalized fractional nonlinear wave equation, we have almost sure global opposeness, and we also have the invariance of the Gibbs measure. So thank you very much for your attention, and sorry for going over time.
Thank you, Professor Oana. I would like to ask you if this argument that you stopped just there, how would you say in a few words how it is applied, and if it's easily also applied for some stochastic equation? And I see Professor Hua is saying that there's another video for questions. Is that so? No, just that, just to continue with that. Okay, how would be, in the case of stochastic equations, this argument? And so just for us to complete.
So what is behind what I've just said? So as I was saying, we try to kind of project on the first and Fourier frequencies. So we have now a finite dimensional system. For that one, the Gibbs measure is invariant. We have global opposeness, but a priori one doesn't have. So if we project onto the first and Fourier frequencies, we don't necessarily have a priori some uniform bounded n. Okay, so the key is exactly that, to say, oh, I can kind of work a little bit and use the invariance of the Gibbs measure in this finite dimensional setting to prove some uniform in n bounds on the HS norm of kind of the corresponding solution. And that's kind of really the key. If you can prove some uniform bound on the HS norm of the of those kind of truncated solutions, then you would use that. You would use the fact that this truncated, the solutions of this finite dimensional system converge uniformly to the solution of the PDE. And there's also some weak convergence for measures. So using this basically three things, you would be able to say that whatever happens for the truncated finite dimensional models will also happen for the PDE.
Also, Luis here in the chat is asking if this whole procedure is applicable to other Hamiltonian PDEs.
Yes, actually, to be honest, I'm not so familiar with stochastic PDEs, but at least in this setting with random initial data, yes, it's quite a general procedure, and it's been applied to many settings, indeed.
very awesome ideas to construct this probability measure. It was awesome.
Yeah, going back to Bourgain, and then I think people capitalized on it and used it in many settings.
So now this becomes a tool to other PDEs, of course.
Yeah.
Great. Other questions and comments? I have another question that would it be possible to consider Hilbert-Schmidt operators as being the space where you're going to consider solutions or whatever?
Hilbert-Schmidt operators.
That would be like summable operators in the sense close to small L2, and just because the norms are so close to the L2, and since you were using them, but you were restricting to Sobolev spaces and this kind of stuff, I was thinking if probably there's a way, but I don't know how to extend this to other spaces. Because I'm always looking for rough solutions, and you were kind of trying to have a balance between roughness and regularity. So I saw that you have an issue in that. Maybe address something.
So for me, to be honest, I feel like this is quite the simplest setting, right? To just have this, standard Sobolev spaces. But yeah, one could consider maybe other spaces and still get this type of results. Yeah, I'm not sure how kind of Hilbert-Schmidt operators could be kind of
probably, yes,
set up here, but
yeah, thank you very much. Any other comments? So thank you very much again, Professor.
Thank you very much.
It was a great pleasure to have you here to listen to your really clear talk. Thank you.
Thank you very much for having me.